Hi, I've snuck into the chemistry lab today to give you a quick orientation on some basic principles of chemistry that will help us as we move forward with our biology. And the first thing we want to make sure we understand is what is an atom. Atoms are fundamental building blocks to chemists, just like cells are the fundamental building blocks to biologists. And essentially, we only need to worry about three types of subatomic particles, or things that make up an atom. The first two are the protons and neutrons. Protons have a positive charge, while neutrons are neutral. The nucleus, the core of any atom, is made up of those protons and neutrons hanging out in a very dense space there. The third subatomic particle we need to be concerned about is electrons. The electrons are negatively charged, and they can be thought of as orbiting that densely charged nucleus of protons and neutrons. What makes one element different from another? It's in the atoms, and more specifically, it's in the protons. The number of protons in a given atom tells you what type of element you're dealing with. Conveniently, the number of protons, also called the atomic number, also gives you a good idea how many electrons a given element typically has, a given atom in that element typically has. For example, we might look at a handy periodic table and see that the atomic number for oxygen is 6. This tells me that normal oxygen, the most abundant form, has 6 protons and 6 neutrons, and then 6 electrons orbiting that atom. The important thing about understanding electrons is it helps us predict bonding. Bonding just describes how two or more atoms are going to interact with one another. And this quarter, we'll be thinking primarily about 3 types of bonds. We'll want to understand ionic bonds, covalent bonds, and hydrogen bonds. So let's start by taking an example of an ionic bond. To understand any of these bonds, especially polar and covalent and ionic, you need to understand what the electrons are doing. Those electrons are not just orbiting that nucleus randomly, they're orbiting at specific energy levels, or what are called orbitals. And the important thing about your orbitals is they each hold a set number of electrons. The innermost orbital, or shell, where the electrons can orbit, holds 2 electrons. The next available shell holds 8 electrons. And this is important to us because elements, atoms, are most stable, or happy if you like, when their outer shells are either completely empty or completely full. So if you consider, for example, sodium. Sodium is abbreviated Na on your periodic table. So check out your periodic table, find sodium, it's way on the left side there, and think about how many electrons sodium has. Looks to me like sodium has 11 protons and therefore 11 electrons. So if I know that 2 of those are 11 are in the inner shell, I've got 9 left, 8 are in the next shell. There's 2 full shells. That's a fabulous situation. That's 10. Sodium has 1 lonely electron. Sodium is going to be much more stable if it can get rid of that 1 extra electron. So bear that in mind. And now check out your periodic table. Look for chlorine. Chlorine's going to be way to the right on your periodic table. It's got an atomic number of 17. It's got 17 protons and 17 electrons. What this is going to mean is we're going to fill that inner shell completely. There's 2. We're going to fill the next shell. There's 8 more, for a total of 10. And now we've got 7 more for the next orbital. Chlorine would be so much happier if it could get just 1 more electron. So, you see maybe a good deal here between sodium and chlorine. If sodium gives up an electron, which it does easily because that makes it more stable, and chlorine accepts an electron, which it does easily because it makes it more stable, we've got the basic setup of an ionic bond. If sodium gives up an electron, a negatively charged electron, it is now going to have a positive charge. It's got 1 more positively charged proton than negatively charged electron. Likewise, if chlorine picks up an electron, it's now got a negative charge. It's got one more electron than proton. These two now have opposite charges, and as you might have heard, opposite charges attract. So that positively charged sodium is going to be attracted to that negatively charged chloride ion. An ion is just an atom that's gained or lost one or more electrons. So that attraction of opposite charges there forms an ionic bond, one of our three essential bond types. You can think of it almost as an act of theft. One atom has stolen an electron from another. Because of that theft, those opposite charges create an attraction between the two. The second major type of bond we're worried about are covalent bonds. Covalent bonds are sharing of electrons, like two little kids sharing a candy bar or playing tug of war for a pair of electrons. So in a situation where each atom needs just perhaps one more electron, two atoms might come together and share that to create a filled outer shell. You can think, for example, about hydrogen. Hydrogen has an atomic number of one lonely electron out there in that first orbital that would be more stable with two. So two hydrogen atoms can come together, share that pair of electrons, and be very stable. We call this a covalent bond, when two atoms share a pair of electrons. That covalent bond from shared electrons could be what we call polar or non-polar. Let's consider non-polar first. If those two atoms have equal attraction for that electron, they're going to share those electrons very equally. We call that a non-polar bond. If, however, one of those atoms has a far greater attraction for electrons than the other, the sharing won't be so equal. Our tug of war won't be so equal. One of those atoms will have a slightly negative charge to it because it spends more time with those electrons. It's winning the tug of war in the covalent bond. Conversely, the other one will have a slightly positive charge to it. It's losing that tug of war. It doesn't spend as much time with those shared electrons. This is important to us because it's going to lead us right into the third critical bond, the hydrogen bond. So I've got a water molecule here. Maybe you can see it, maybe you can't. If you can't, draw it out, work with me here. I've got an oxygen atom, and it's bonded to two hydrogens, an H2O, or a water molecule. These are covalent bonds, but they are polar covalent bonds. Oxygen has a much greater affinity for electrons than hydrogen does. So this oxygen will have a slight negative charge to it, while these hydrogens will have a slight positive charge to them. So you can imagine now that if I bring two water molecules together, these slightly positively charged hydrogens will be attracted to these slightly negatively charged oxygens. There's an interaction that occurs there because of that attraction, and that's what we call a hydrogen bond. And that's really critical to understanding the behavior of water. Water molecules interact with each other in lots of unique ways because of their forming of hydrogen bonds. So there's your basic principles. We need to know what an atom is, we need to know what bonds are, the relative strength of these bonds, these really strong covalent bonds, reasonably strong ionic bonds, and much weaker but very important hydrogen bonds. This information will carry you forward and help you understand the four basic biological molecules that we'll meet next: your carbohydrates, lipids, nucleic acids, and proteins. Stay tuned.